Good morning, good afternoon, good evening, everyone. Thank you so much for joining us today. I am Reginald Hammah with Rocscience in Africa, and today I'll be joined by Neil Barr from Georeferencing. This webinar, which is part of the Rocscience webinar series. In this particular series, we'll have people from Rocscience collaborating or cooperating with people from industry and presenting some relevant topics to you. For today, we are talking about advances in open pit modeling and monitoring. Again, I am Reginald Hammah with Rocscience Africa. I will be talking about a recent advance in slide 3, which has to do with building models from block models. So if you already have a block model at a mine, for example, we will look at how you can build an open pit model out of that, and then we'll analyze it and look at results. We'll compare the results to an original file that has the real geometry and see that we do not lose much when we use the block modeling, but it offers us speed advantages. So that is what I will be talking about. Another thing I wanted to let you know is, as we present, if you have any questions, you can ask them, you can type them on your screens, and we'll do our best to answer them. And we are very open to ideas, so if you have any new ideas on what we can do to improve what we are showing you, please let us know, and we will be very happy to incorporate them in future developments. So I'll let Neil introduce himself and his topic.
Thanks, Reginald. Hi, everyone. Neil Barr from Gecko Geotechnics. At Gecko, we do practical and innovative geotech solutions for the civil and mining industries. We primarily focus on open pit slope design, and today I'll be talking about basically integrating monitoring and reconciliation processes to improve slope stability model reliability. And it's something that you can all try at your mine sites or in your consulting work yourselves as well. Thanks, Reginald.
Thank you very much, Neil. So what I'm going to do is I'll just stop sharing my screen for 1 minute, open up all the screens that I'll be using for my portion of the webinar, and then I'm going to cast to the screen again. So just bear with me for 1 moment. Okay, so what are we going to be doing today? I'm just going to show you. This is a slide 3 model we built. Let me just go to the geometry screen so you can see. So it's an open pit with multiple material zones. So there's a host rock. In this case, it's a sandstone. There's a mafic intrusive, and there's a phyllite zone. So that is the material. These are the material zones for this particular pit example we will be looking at. Now, this is the way we have always built our slide 3 models to date. We build the external geometry. We also get the volumes, the geometries of the different material zones. We import them, and then we do divide, or we create our 3D slide 3, our slide 3D model out of that information, out of that geometry, which is very good. But sometimes what happens is, at a mine, they have this same geometry with a different material designated in a block model. And as we go through this example, you will see that that offers some advantages. Yes, it is an approximation to the current problem, but it offers several advantages in terms of the speed and ease of building models. So we are going to look at that. So I will bring in a geometry. I will then also import a block model for this site, and then create a 3D slope model out of that information. And we'll compute it. And then we will compare the results to the results we get from using, let me call it the true model, just because it uses a true geometry. We'll compare our block model to, just in order to give the name, to the true model, and we'll see what are the differences in the answers, or how close the answers will be to each other. So I am going to start with, I have a base file, and if you were running something like this, you will be doing something similar. You would have built a geometry, an external boundary. So that is what I am showing you on my screen. And then I am going to bring in a block model. I'll do a divide all. When it gets to the time where we compute, I will actually just bring in computer results. It takes about 4 minutes, but we don't want to sit and wait for 4 minutes. So I'll bring in the computed model so you can see what the results look like. So the first thing I'm going to do is, as I'm showing here, I have my external model volume that I have brought in. Now I am going to import a block model. The way we go about it is just go to your material properties dialog. I can access it either directly using this button, or I can go to the materials dialog and choose define materials. I'll end up in the same location. And then what I have done is I told you the different types of rock masses we'll have in this model. There is a sandstone, there is a mafic intrusive, and there is a phyllite. And I've already defined their properties in this model. Now I am going to bring in the block model that contains information on which blocks have which of these materials within the blocks. So to do so, I'll first select material number 4. It's a default parameter material. We haven't done anything with it. So I select it. If it wasn't here, I could have added it from this dialog. So I bring in this, I highlight this material, and then please look carefully how we will import the block model. Please go to the strength, make sure you're on the strength tab, and then you go to failure criterion. And there we will go to the bottom of the list. There is an option called block model. So I will select this block model. The dialog changes and it has an area we call the new function. So I'm going to import my block model into this new function. I could change the name if I wanted to. But to bring in import my block model, I will select the edit button here. So I click it and a new dialog opens up. And this dialog allows me to import a block model. So I have a block model for this site, and I'm going to import the model right now. So let me click import block model, and it's asking me to navigate to the directory with the block model. I have it right here, so I select it. And then it's in the CSV format. So let's take just a quick minute to look at the information that is in that block model file. I have my centroids of each block, X, Y, Z, so in 3D, X, Y, Z. And then I have the size of each block. Those are my DX, DY, and DZ. And then last but not the least, I have a column that lists what material is within the block. And they have the material names that I showed you earlier. I will change, when you look at the number of rows that are visible here, you see that the data starts from row 8. So I'll come here and say my data starts from row 8. On top of that, when I look at the number of columns, it's 1, 2, 3, 4, 5, 6, 7. So my material data is in column number 7. So I'll change material to column number 7 and see what happens to this column here when I do that. When I change to column number 7, it lists the material types. So that's the first step we take, and then we select OK. So now it's importing the data. We saw the wheel spinning for a while, and then we get this dialog. Sometimes, and depending on how the block model was generated, we could try with estimate parameters to quickly input the relevant data we need to insert this block model in the geometry we already have. And we will have to define how we would want that data to be taken from this spreadsheet that we are importing. In our case, we are going to use the default. We'll specify block size in blocks, and minimum corner. Now, all of that the information is already here. In cases where the estimate parameters work, you just click it and it will populate this portion of the dialog. In our case, it has not been successful, but no worries. What we now have to do is put in the information. This gives us a chance to understand what the information is. This row here is listing the different types of data that I will need in this area of the dialog. Number of blocks, that will be calculated, so I don't need it. The next one is rotation. The rotation is 0, so I don't need to change that value. The next option we see is the block size in the X direction. that value is right here. So I will copy it in this case and paste it here. This is the size of the block in the Y direction. I will copy it and I will paste it right here. And this is in the Z. Again, we'll copy and paste it. The next thing we have to do is the number of blocks in the X direction, Y direction, and Z. That information is right here. So in the X direction is 200, in the Y direction is 300, and in the Z direction it's 50. These are the number of blocks in the data. Last thing we need is the minimum corner of the block. So again, that information is here. This is the X for that minimum corner. This is the Y, and I put it here, and this is the Z. So if my estimate parameter had worked, it would have automatically grabbed this data and put it here. Due to different formats from different software, sometimes it may not do it automatically. Now that I have brought it in, I just want to check to make sure that indeed these parameters are right. So I will validate my parameters. So I'll select validate. So it's doing a check, and it comes back to say all the blocks conform to the parameters. So I've chosen everything right. At that point, I will select OK to close the dialog. I get this is just a piece of information saying a brief description of the import process, and I'll select OK. And now once I select OK, it updates this, and I see my 3 materials listed here, and all the information are listed is also shown here. And again, I select OK. So by doing that, I have imported my block model into the dialog. It took a little while because it was updating everything. Now all the same information is in this portion of the dialog, and I can select OK to close it. So now what I have done is I have imported a block model. Now let me tell you something briefly about this block model. All the blocks are the same size. For now, that is what we have. The blocks all have the same size. And in the future, we'll see ways in which we can incorporate ways of bringing in variable size blocks. But for now, it's the same size blocks. So I have imported my block model. I've closed the dialog. The next thing we do is we need to create a geometry out of that block model. And the way you do that is go to the geometry dialog, and there is an option that says create external from block model. So I will select that option. So now it's creating a geometry out of the block model. It will take us just a few more seconds, and we'll have that geometry ready. So it's doing that still, but you can see already this is now jagged because it's bringing in blocks. So the block model has been brought in. As you can see, you can now see the different material zones, the yellow, the sort of purplish, which is the phyllite, the yellow is the, I believe is the mafic intrusion, and that's the surrounding sandstone host rock. So it has created this geometry out of the block model. Once we have the geometry in, as you know, with our 3D software, we have to do a divide all. So I'm going to do divide all right now. So I'll select divide all, and I'll use the default settings. So that should take me about a minute, a little less than a minute. But what it's doing is it's dividing all the geometries so that we'll have several different volumes. When this step is done, sometimes you end up with several small volumes. If that happens with our case, we have a tool that allows us to reduce the number of volumes without compromising the accuracy of our solution. So we will do that at the end of this operation, where we would have divided all the different parts of the model. So we are almost done. Okay, it's doing some intersections, it's creating the volumes, and we will be ready to go. But as you can see, if you have ever tried to build models using the original geometries, many times those geometries are not very nice, especially in 3D, and geological models just tend to be sometimes very complicated. Cleanup alone can take you sometimes several hours through no fault of the program. Everybody who has done 3D geological modeling will be very conversant with these problems. So whenever you can use the block model, you can save yourself a fair bit of time, at least as a first iteration to looking at the stability of your pits. You can use this model. As we said, Divide All has created many different subvolumes. So what we can do is we use a tool called collapse small volumes to reduce the number of subvolumes we have in our model. So to do that, I'll go to geometry, go to repair tools, and select collapse small volumes. And I get a dialog that allows me to choose how I want to collapse the volumes. I will choose advanced filtering in this case. And so it has listed for me all the different volume sizes, and I see a chart. I will go straight to this side of the chart. I'll just do it graphically, choose something here, which takes out all the tiny ones. So it's listed them, and then I'll choose collapse. So many of them, the ones we are seeing now, have volumes of about 1 cubic meter, 3 cubic meters. We don't need that in our model. So now it has collapsed them into just a few volumes. That is what we have obtained right now. Now I can click close to end that portion. And then let us never forget to save our models. So I will save my model. Once I have saved my model, I am ready to compute. It's that simple. Before I compute, let's just review our slip surface options. So I bring up my slip surface dialog. We're looking at an ellipsoid. We are using the cuckoo search method, and we are doing surface optimization. So I'll just select those defaults. I am okay with it. And at this point, I am ready to compute. I can go to compute and click compute. For this particular model, compute will take about 4 minutes. And I don't want us to sit and wait for 4 minutes for the results. So I have already computed the model. And this is the computed model. So let me maximize the perspective view. So that is what we see. And right now we are looking at the Jambu failure surface. I can switch to the Bishop. The Bishop factor of safety is 3.8. The Jambu was 3.72. So these are the results we got from using the block model. I am now going to show you the same model, but using the complete model. And let's see how the results compare. So I'm going to have a split screen mode. Let me maximize this perspective view and go to results. So if I switch to the Jambu, right, I'm seeing the Jambu results. The complete model is got a Jambu factor of safety of 3.73. The block model has a factor of safety of 3.72. Not bad at all. Now let's try Bishop. When I go to Bishop, again, the complete model has a Bishop factor of safety of 3.85. The block model has a factor of safety of 3.82. Again, very close. If I look at all views, you can see that it's in the same area of the pit. It's near identical failure surfaces. So this is what we have done with the block model option. As I said, this is version 1. You've seen how we've implemented it so far. If you have any thoughts, please let us know. And we will include your ideas in the next version of the block modeling tool. But I encourage you to try them, especially those of you in mining who have block models. And let's see how easy it makes your life. Thank you very much. We will answer questions at the end, but at this time, I would want to hand over to Neil to present his portion of the webinar. Thank you. Neil, I'm going to make you a presenter.
Thanks, Reginald.
Go ahead.
Okay, is the screen up? Okay, I hope you can see my screen. My presentation today is on monitoring and reconciliation and how we can use these methods to improve the reliability of our stability models. So just a brief outline of the presentation. We'll just briefly go over the rock mechanics process specific to open pit mining, discuss the need for model calibration and reconciliation. I'll show you a couple of case studies of how we apply this method and go through a couple of key points at the end. So in almost all large mining companies, the rock mechanics process is iterative. It involves site investigations to develop a geotechnical model, which has some uncertainty and limitations. And then there's a design acceptance criteria, which the mining company selects to adopt based on their risk acceptance. After that, slope stability models and analyses are undertaken, excavations begin, and risk management begins. Risk management typically involves deformation monitoring, groundwater monitoring, and reconciliation. So just a quick note on the importance of safety monitoring. This is a case study from 2 weeks ago from Bingham Canyon Mine in America. Some photographs from the AGU blog and Professor Brad Ross. So most economic pit slopes accept a certain amount of failure. For example, 10 to 30% of benches or 3 to 10% of interramp slopes. In these photographs, you can see an interramp slope failure. They're acceptable provided that safety risks can be managed well. And in this case, I really want to congratulate the Rio Tinto Bingham Canyon Geotech team for this excellent example of safety critical monitoring and risk management. They really did a terrific job keeping people safe. Now, all models are wrong. Some are useful. And with this, I refer to geotechnical models, which are built up from geological or lithological models, and also incorporate major and minor structure, rock mass, and groundwater. So why are they wrong? Well, in geotechnical engineering, we have very different challenges to civil engineering and mechanical engineering. We have data collection in very complex systems with limited spatial data availability. And based on this, we make our geotechnical models. We then have modeling limitations for large excavations, whereby we assume a continuum or a rock mass, rather than a discontinuum or intact rock pieces and discontinuities. We also have data uncertainty and residual risk. And as a result, we monitor for safety risk management. So uncertainty in geotech engineering. The level of uncertainty basically depends on what we know and don't know. So low uncertainty is where we have known knowns, things we know that we know. So for example, in a tunneling scenario, that's the alignment of the tunnel and the depth, the basic geology. In a mining open pit scenario, it's the same thing. It's the location of the pits, the location of the ore body, its orientation, etc. And then we have things that are called known unknowns. So things that we know that we don't know, and we can then go and investigate them. So basically all the features of our geotechnical model typically fall in that category. But we also have unknown unknowns, things that we don't know that we don't know. So these are typically discrete hazards or geological anomalies that we didn't expect. So the need for monitoring and monitoring to do model calibration and reconciliation. Basically, we can develop slope stability models with no calibration, qualitative calibration, or quantitative. No calibration basically means we run a model based on purely on subsurface site investigation data with no calibration at all. Qualitative would be modeled failure mechanisms confirmed by field observations or monitoring results or failure back analyses. And this is what I'll talk about later in the case studies. Quantitative is basically where we do a fully calibrated model with observed displacements and or stress measurements. And such models need to be updated as excavations or study phases progress. They can be reconciled with an ever-improving understanding of ground conditions as they're exposed. So our first case study. We're going to look at ductile deformation of an unstable slope. This case study is from Papua New Guinea in Southeast Asia. Here we have a very weak, low stiffness rock mass. It's saprolite-like. It's a seismically active region, and rainfall exceeds 5,000 millimeters or 200 inches per annum. The focus is on the western slope. And the monitoring systems available, ground-based synthetic aperture radars from IDS Georadar. In this case, they're using, in this case study, they're using an IBIS FM with a scan frequency less than 7 meters. They're now also using the ArcStar radar, which is even faster. And this data provides one-dimensional line of sight deformation. They also use prism monitoring, The prism monitoring is fully automated using Leica TM50 total stations. Basically, they read the survey prisms approximately every 3 hours, sometimes a little bit longer. And the prism density or spacing is 50 meters typically. And in areas of interest where hazards are identified, more prisms are installed. So initially, this part of the mine was designed using 2D limit equilibrium cross sections, assuming isotropic ground conditions and with the absence of geological faults, which at the time were unknown. Hydrostatic pore pressures were also considered, and these were probably optimistic given the rainfall. When the same model inputs were put into a 3D model, they achieved a factor of safety greater than 1.4. In 2D, they were 1.3. Now, for the context, here's a photograph of the slope. So above the slope is infrastructure, a pit perimeter drainage system, and a permanent access ramp. So the slope was constructed and stable for a few weeks, and then the synthetic aperture radar detected movement. Here you can see some of the deformation hotspots on the right-hand side, the red areas. So the IBIS FM identified linear acceleration, ductile behavior, and after a field investigation was undertaken, between 20 centimeters and half a meter of cracking was identified behind the crest. And relic geological fault was found dipping into the pit. Pore pressures in a nearby VWP were also quite high, indicating fully saturated conditions. So the same radar data, basically over that time period, it identified 500 millimeters of line of sight or LOS displacement. And you can see the notable change in velocity on the 16th of October there. At the same time, the prism monitoring, which was a second layer of defense in this case, also identified the same response in behavior based on prolonged rainfall. So what you can see here on the right is prism vectors, with the red ones being higher magnitude displacements. And the prism monitoring data itself, looking at 3D vector magnitudes, you can basically see the same linear acceleration at about the same time. In this data, because it's three-dimensional data, you can see the actual magnitude is double what the line of sight could see, just because of the positioning of the radar relative to the movement direction. So aerial photogrammetry was undertaken using a basic drone from DJI and photogrammetry processed in shapemetric software to model the actual fault planes that are visible in the slope, which were not identified during drilling campaigns. It basically identified several low-angle faults that were dipping to the east or southeast, and these are really difficult to map in smooth faces that are in saprolitic material. The infilling characteristics, however, were obtained from mapping. The model was then revised to include a low-angle geological fault and back analysed until a factor of safety of about 1 was attained. So with the inclusion of the fault, basically the factor of safety in the model reduced from 1.4 or stable and meeting the design acceptance criteria to slightly above 1. Now remember, it's only moving, it didn't fail, it's quasi-stable at this point. So a validation step between the radar data and the stability model showed that the deformations hotspots had a reasonably good correlation with the low factor of safety area. The same model was then run using finite element in RS3, and it identified a lower critical strength reduction factor, suggesting failure had occurred. And it identified shearing preferentially on the fault plane, which is as expected. And then comparing the total deformation from RS3 to the radar data, we found that the hotspots didn't quite match perfectly. They had the general same properties in terms of area and magnitude of movement, but the patterns weren't perfect. As you can see on the left, there's more deformation shown in the entire slope in the numerical model. So we started a remediation plan, radar monitoring with tarps and alarms to keep people safe, and started doing horizontal drilling for depressurizing the slope. This was incredibly effective. Basically, after the horizontal drains were drilled, the movement almost immediately stopped. Some key points from that case study. The monitoring identified a deviation to expected ground behavior. That was the radar. It was then confirmed by prisms as a second layer of defense. This prompted a review of ground conditions and a review of stability models. The qualitative validation between the monitoring and models were critical in understanding that the model makes sense and the depressurization stabilized the stope. Our second case study. This one uses INSA, or satellite INSA rather, to unveil unknowns, enabling a response to slope design. So this is a case study from Australia where there's multiple open pit mines in a large deposit. Spatial monitoring is a challenge. Very limited capability to put in ground-based monitoring, especially for small pits. The ground conditions are highly anisotropic, although the geological conditions are similar across many pits and material properties are understood quite well. So basically the monitoring system uses INSA, in this case the provider's Trial Tamira, and a dynamic monitoring and trend variation analysis service is used. So time series data is collected every fortnight. The details of the INSA are here, but basically it's using dual orbits, ascending and descending at high resolution to provide one-dimensional line of sight information as well as two-dimensional data, vertical and east-west deformations. So this is an example of this case study. So you can see in the image on the right, a red hotspot shown by the INSA data. Now this is showing line of sight data with deformation moving away from the satellite on the south wall of one of the pits. As I said before, this is a commercial service provided. There was no further interpretation done of the INSA data other than what's available. And basically what that data, when you look at an individual point there, showed was changes in displacement rates basically coinciding with every time mining activities occurred near that south wall. So stick split behavior in alignment with mine progression. So originally this pit was designed using two cross sections, or this portion of the pit rather was designed using two limit equilibrium cross sections with factors of safety greater than 1.2. Reviewing the same pit in 3 dimensions with the pit floor shown here at the time of deformation, we were able to get another result. So that's the future excavations proposed. And basically overlaying the deformation data on that convex slope profile at the time where the pit floor was as shown, shows the hotspot of deformation. Running the model in 3D with exactly the same inputs as 2D, the only difference is the geometry was 3-dimensional, found a factor of safety of just under 1 in that area, with a projection to possibly have a failure if the next bench was mined. Key points from that study. INSA was able to identify deviation expected ground behavior. Again, unfortunately, because of the amount of pits there, it was not possible to have monitoring from a ground-based system. This enabled the planning and deployment of ground-based systems, and radar and prisms was used after to manage the risk. And it also prompted a review of ground conditions and a revision of stability models. But basically, that 3D model showed us something we didn't know from 2D from years before when the mine was designed. It found opportunities to adjust the mine design and decouple the slope and prevent collapse. Our final case study is a large open pit model calibration. So this is from a case study in Africa. Pit slopes here exceed 400 meters. It's a very strong rock, high UCS, weak foliation, subparallel to the interramp angle. The slopes are basically structurally controlled. Monitoring is with a ground-based real aperture radar, and the area of interest shown in the photograph is basically driven by the foliation and a pervasive joint acting as a release plane. So the monitoring system used here is Reutech's MSR, a trailer-mounted one-dimensional line of sight radar system with scan frequencies much less than 15 minutes. So a local model was developed using 3D limit equilibrium. It's shown here. It used anisotropic material strengths for the foliation, a joint plane for the release plane, and no spatial constraints. Groundwater was modeled based on finite element simulations. This model literally took 2 hours to develop and about 30 minutes to compute. Pardon me. The factor of safety in the model here is about 1.02, basically 1. So the validation step is basically to import the radar data where we're seeing deformation hotspot collected over an 18-hour period over the model results, and the displacement hotspot had almost perfect match with the low factor of safety area. In plan view, on the left, you can now see the modeled slip surface, and on the right, you can see the deformation hotspot from the radar data. So again, a pretty good match. So we took that model and that calibration and expanded it to a global model, or a mega model as we jokingly call them. So again, same sort of input parameters, but the model's calibrated, particularly in that material type. This took approximately 2 weeks to develop, and the model has over 10,000 individual components. Computational time is still about an hour, but basically total time to a result, about 2 weeks. So here's a translucent version of the model, so you can sort of see the detail that actually goes in behind it. They have very complex geological conditions, and you can see the minimum factor of safety slip surface there, which is basically identical to the one in the small model. In opaque view, you can just see the surface geology and the pit geometry much better. And then overlaying the radar data from the Reutech radar, initially as a point cloud to see the hotspot, or as a textured mesh. And that's the qualitative validation step that you can perform. Just zooming in on the larger model, you can see the joint trace behind the slip surface limiting it, and the radar data overlaying. There's the fault plane, the joint plane a little bit more clearly. So, some key points from the presentation. All models are wrong, some are useful. In my opinion, calibrated models are certainly more useful and more reliable than uncalibrated ones. Qualitative modeling is relatively fast and simple, provided you have monitoring data available. And with some INSAR services, if you have the ability to process yourself, there's free data available online. Integration doesn't only include monitoring and modeling. Geotechnical model reconciliation is key. So as you progress excavations, you have a lot of opportunity, especially with improving technologies such as photogrammetry and laser scanning, to rapidly assess geological and structure conditions and update the models as you go. Traditional face mapping is still needed, especially for our intact rock property validation and our geomechanical properties of structures, which aren't accessible from photographs. Fault pressure monitoring we found in many mines is a gap, but something you can also remediate. From Stephen Hawking, the greatest enemy of knowledge is not ignorance, but it's the illusion of knowledge. Please don't fool yourselves into thinking that even the best model you make can be right. The geology might still be different. Thank you very much, Neil from Gecko. And if you've got any questions, look forward to a discussion.
Thank you very much, Neil, for your excellent presentation. While the presentations have been going on, there have been a few questions. So I'm going to go through just a sample of them and just read a question and we'll tell you what the answers are. But again, even after the seminar, if you have any questions, please do not hesitate to let us know and we will address them. So somebody asked a question. Is it possible to import, okay, first is, does this process work only with models in CSV format? At the moment, yes. But I believe there are also text versions that can be managed. So yes, and with time, we will add more formats. Is it possible to import a block model of GSI or RQD, or would that create too many different volumes? Right now, there are no limits to the number of volumes that you can model. But just remember that you must have IDs. Currently, it's material types we are dealing with. We intend to do the block model so it can also handle individual parameters. But right now, it's driven towards handling a suite of parameters that comprise a material model. So that's what it is currently, but as we said, this is only version 1. It will be changing. Is there any program that can provide us with a block model file in CSV format? The geological software, CellPack and DataMine and Vulkan and Mine? I've forgotten the name. Anyway, there are several of them. So yes, the mining software and the geological software will allow you to create these block models in CSV formats. Somebody asked the block model based stability analysis, or the analysis we looked at seems to be based on you know, the Bishop and Jambu. The first question is, are there developments to combine this with numerical analysis? And then can we use it for tunneling? And the answer is yes. We are planning to implement this in our 3D finite element software, RS3, in the near future. So we would have this feature in RS3. Once it gets there, it means we can use it for tunneling and all other kinds of underground excavations. So it's heading towards that. We are heading towards using it for numerical modeling as well. It's the same thing we mentioned here. For all slopes, the question says, should we check both the stability along discontinuities using dips, S-wedge, rock plane, rock topple, and then the global stability? And the answer is yes. We have to check the stability of the slope, and the behavior varies at different scales. So for example, at the bench scale, we tend to get behavior that is generally driven by discontinuity. So you use your S-wedge, rock plane, rock topple. Then as you go deeper, by the time you get to overall slope, and if you have a large slope, then you realize that there are methods like slide 2, slide 3 coming. But we need to use all these tools to analyze the different mechanisms. Even at the overall slope, if you have faults that intersect, they can form wedges. So even for an overall slope, we may have to use an S-wedge or some form of discontinuous analysis to examine the behavior of that wedge. So even that we can do. And yeah, that's mentioned. So those are the questions I have for now. I will hand over to Neil. Maybe Neil, if you have a few more parting words. But one of the things is we can import radar data, and Neil did show a bit of that in his presentation. So both slide 3 and RS3 can import information from radar and superimpose it on your pit, so you can look at some of your monitoring information quite readily and compare it to your numerical analysis or limit equilibrium analysis. I just wanted to throw in that. But if you have more questions, there are a few more. Let me see. Somebody's asking, what is the future scope of 3D modeling for open pits? Neil, do you want to take a first stab at that? Where do you see the future of 3D open pit modeling going?
Well, I think all pits will be modeled in 3D. Basically, the only change between 2D and 3D is the geometry. And you'll see that all your colleagues in technical services and mining, it's mining engineers, surveyors, geologists, groundwater modelers, everyone's operating in 3D. Geotech has chosen to stay a little bit behind, but now has the opportunity to catch up. You probably saw some of the model times, development and run times. They're pretty quick. I don't think that's the future. I think that's today. And this block modeling tool is certainly going to unlock even more opportunity to do 3D modeling faster and more routinely. So for example, with quarterly mine plans or annual mine plans and phase positions, you'll be able to do checks for your risks and opportunities by rerunning your stability models in 3D.
Yeah. All right. Well, thanks, Neil. And I agree with Neil. Actually, we were having a chat yesterday, Neil and I, and we were talking about this. And one of the things we said was 3D modeling is getting to the point where it is routine. As Neil said, I mean, it may not be as simple as the 2D because we are so used to 2D, and 2D is less complicated. I agree. But we are getting to the point where the tools are becoming quite easy to use, and we can do 3D. And it does not require supercomputers to analyze such problems. So it will become more routine as we go along. The other part about 3D is You know, in 2D, we have to select the critical sections. And a lot of times we think we know. But the more we use 3D, the more we've seen that at times the sections we select as experts and believe are the most critical aren't the most critical. Selection of most critical is not as easy as it seems. 3D will shed some light on that, but we'll continue to use 2Ds. I don't think 3D tools are ready to replace 2D. 2D is still very fast, and we can do a lot of sensitivity analysis with 2D. But we see that we'll be combining the tools. And remember, in 3D, you can just take cross sections and you analyze in 2D straight away. You can take a cross section from slide 3 and analyze it in slide 2. So it saves you the time of even building your 2D cross section. Same with RS2 and RS3. So that's the future. The future is here and we'll use it more. It's not ready to replace 2D yet. I don't know or whether it will ever replace 2D, but it will be a good complementary tool. That would be my answer. One of the viewers is asking about how we do georeferencing. I think, Neil, this might be more up your alley. I'm sure it's got to do with monitoring. You want to say something?
Sure. Yeah, look, so for prism monitoring, typically prisms are in a local mine grid setting. All the radars from IDS, the ARCSARs, the IBIS FMs can very easily be geo-referenced to your local mine grid in the Guardian software. The Reutech radars also can be geo-referenced with survey controls, so they can be in your mine grid system, as are all your geological models, your mine designs, etc., that you build the stability model from. So everything's in the same system. It integrates quite seamlessly. The only one you might have some issues with, and it's not really an issue, is INSAR data. So you just have to talk to your INSAR service provider and do the coordinate translation from their latitude and longitude to the mine grid, and that's something that they'll provide for you free of charge, typically with TRE Altamira or 3V Geomatics, sort of the two big providers. So it all works in the same system. The benefit there is when you build your model in 3D, and you can also, as Reginald said, cut 2D sections from it and continue analyzing in 2D, is when you start to find new geological features in your mine as you excavate, you can capture those, create a wireframe, and import them and add them to the model. So you don't have to rebuild your model once you have it. You can just continuously add more and more detail as you go.
All right. No, thanks, Neil. Then there's a question of, are there features in RS2 and RS3? Sorry, where is that? I've lost the question. Are there features in RS2 and RS3 that may include probability of failure or stochastic inclusion of failure? RS2 already has that. You can do probability of failure in RS2. It's all got to do with computational time. So as computers get more and more powerful, and now there are routine computers that have 64 cores, and they are becoming more and more affordable. As these technological advancements come in, I think you'll see more probabilistic modeling in numerical methods. But for now, you can do it. It just takes more time, and you need to be wise in terms of how you do it, so you don't waste too much time and lose time actually trying to gain insights. That will be my thoughts on that. Neil, do you have any thoughts on that?
I agree completely. Look, it's all about computing power for 3D probability of failure. It will get there one day to be automated, but now you'd have to do it, sensibly, maybe with a point estimation method on specific parameters or sensitivity analyses on what could go wrong and what would that mean. You just have to be a bit more smart about it for now.
All right. No, thanks. Is it possible to create a block model attribute into slide 3? Yes. As to how easy it is to take 2D cross sections, I will check with the programmers. I'm not sure we've done it yet, so that I will have to check. But once we've created that 3D model, as I showed you, the block model in slide 3, we can take cross sections and send it to slide 2. So that already exists. Absolutely. Can you bootstrap to perform back analysis using the radar data? We want to do back analysis. Can we use the radar data to do back analysis? Neil, have you tried anything like that?
Absolutely. The first case study and the third case study presented were back analyses of unstable slopes. The second one I presented was also a quasi-stable slope. What the radar data allows you to do is focus in on an area where you're not getting the expected ground behavior, And then you have to yourself, of course, make adjustments to the model where you need to replicate the ground behavior you see. And that will be based a lot on physical observations of ground conditions, what's there. For example, we added a fault in one, and another one that was that joint release plane. It's there as a tool to help guide you in the right direction.
All right. No, thanks, Neil. And then there's a question about the role of a river affecting slopes and underground structures, and which model can we use with remote sensing data? I don't quite, Neil, can you help out here in terms of remote sensing data? Is there anything you can get from that that will show you the influence of a water body, for example, a river on slopes and underground?
Yeah, look, okay, let's tackle one at a time. So riverine erosion causing landslide. INSAR should definitely be able to detect the deformation. You may have to use a different type of INSAR if there's a lot of vegetation, and that's that advice you can get from the service providers. In relation to underground workings collapse, of course, INSAR can also do that. Actually, sorry, back to the river one, ground-based radar, prisms, all of the traditional tools also can do it. For subsidence from mine workings or other underground excavations, if displacements are visible at the surface, INSAR will detect them. It's quite accurate. Otherwise, there's other methods. If you know of an excavation, deep hole extensometers in boreholes, other things like that to look at potential for caving and that.
No, thanks, Neil. And then there's a question on whether slide 2, sorry, whether this analysis we've done is valid for dams. Look, slide 3 can work for dams. Neil's monitoring stuff he's discussed can all work for dams. The
so
issue
we actually
is,
published, we published a paper
go ahead, Neil.
Conference, at the Rocscience conference 2 months ago, looking at dump instability using 3D limit equilibrium calibrated with both INSAR and ground-based radar. If you want to send me an email, and I'll send you more information on that if you like.
All right, no, excellent. Thanks a lot. Now somebody is asking whether slide 2 we know can do transient analysis. Now they want to find out whether slide 3 can. So the first thing I'll say is slide 3 does not do finite element analysis. You will have to do the finite element groundwater analysis in RS3 and import the results into slide 3. Now RS3, similar to RS2, can do steady state and transient. So the answer is yes, we can do it with a Rocscience suite, but for 3D, you can't just use slide 3. You would have to use RS3 as things stand at now. What is the accuracy of the block points modeling with field data you were using? I mean, my blocks were roughly 10 meter by 10 meter by 5 meters. And the answer between that and that of the, let's call it complete model, was very little. The difference was well less than a percentage point. So I would say the block models are quite useful, fast to build, especially when you have a lot of material zones and all that stuff. It can save you some time and you can get reasonable answers and quick. Neil, do you have any thoughts on that?
Yeah, I agree completely. And look, I think there's another piece there where you should talk to your geology team on site, because typically the geological wireframes are either developed from a block model or the block model is developed from the structural wireframe. So those two data sets are completely, they're not independent. So talk to your geologist for your specific case study on site.
All right, thanks, Neil. And then the last but one question. We'll see whether we are almost out of time. But there is a question here on minimum specifications for computers to model. Why don't I start with maximum specifications? I know we've had discussions. You know, we have two main groups of CPUs. The CPU is very important. And we have the Intel CPUs, and of course we have the Ryzens. Quite recently, it seems, and I'm no expert in these CPUs, but it seems the Ryzens have taken the lead. So you can get a Ryzen Threadripper that has 64 cores. Now we've done some testing. So a colleague of mine, Ian Williams in the UK, recently acquired a 32-core Ryzen Threadripper machine. And we checked with my current computer has 8 cores, but it has a slightly higher frequency. So frequency is also a function. But anyway, to cut a long story short, we tested a model, and his is about how many times? It's about 6 times faster than mine, something like that. So it scales up, not linearly, but it scales up quite well. So the 64 core will not quite twice as fast as his, but maybe 1.6 times, something like that. So it scales. That's what I would say. And the Intel, there are some good Intel processors, the i9s, i9, 10, 980. There are different versions. Most important thing, look at the core, but also look at the frequency, the speed of the core. Combining those two, you can get a good idea of the speed up when you use these fast computers. Neil, you have anything to share?
For slide 3 for limit equilibrium, all the case studies I showed you were actually done start to finish on just a regular laptop. I think it cost $2,500 2 years ago. It's nothing special. It's a regular laptop.
And it was still done in minutes, generally.
Yeah, minute. Model runtimes are maximum 2 hours, but you can wait 2 hours for a result. It's not an issue. Model build times were between 2 hours and 2 weeks, depending on the size, but that's due to the complexity, not the software time or the computer time.
Yeah. And you know, that question is also something that we will let the experts of Rocscience come up with some more guidance, and we will post it somewhere on our website, so you can refer to that and get a guide. The other thing I'll add to that is generally, it seems the gaming machines work quite well. So the gaming machines, even the gaming laptops, are generally quite fast because they use very fast frequency CPUs, although they might not have too many cores. Anyway, that's something to consider.
Yeah, Reggie's absolutely right. It's the $2,500 computer is an Alienware. It's a gaming computer.
Excellent. No, thank you very much. There are just a couple of questions left, but we've run out of time. So what we will do is we will save these questions and we'll post them, or we can email those who ask those questions and supply the answers. But thank you so much. It's been a lovely time with you, and we look forward to the interactions. Again, as we said, we've only shared ideas. We have our thoughts, but we know you are super smart and you have some good ideas that could help us. Please do not be shy. Let us know, and we'll be willing to incorporate them into our work. Neil, last words from you.
Thank you very much, everyone. And yeah, look forward to seeing some new ideas coming in and the improvements being made. Thanks, guys. Thanks, Reginald.
Thank you, everyone, and see you next time at the Rocscience webinar series. All the best in your work and stay safe. Thank you.